Hello everyone, welcome back to PC 301 workshop, and we are here with the final talk of the day. And we have with us once again Karthik CS from New York University for the final talk on FPT in approximability. Thank you for joining us, Karthik. Over to you now.
Thank you. So this is the final talk, and I want to sort of tie all loose ends and wrap up with some applications of the inapproximability results we saw in the previous lecture. So the outline was that in the first lecture, we set up with some basics of coding theory and what the max cover problem is, and what the one-sided click by click problem is. And then in the second lecture, we saw how to create a gap, which is and how to prove an inapproximability result for max cover and one-sided by click. And today we are going to see how to translate that gap. So given that we have already created a gap problem, how do you reduce it to another problem which has gap or might not have gap? So the first part of this talk is going to cover proving the hardness of approximation of set cover problem, parameterized set cover problem. And this will go through an intermediate problem called min label, which we'll introduce. And that is going to be the first part of the talk. And in the second part of the talk, we're going to use the one-sided by-click problem hardness of approximation result we got and show its result to by-click. And I'll briefly mention some other applications. And I want to also show a proof of hardness of approximation of click, but not based on W1 not equal to FPT, but a less standard assumption such as CAP-ETH. And finally, I want to state some open problems, mainly stemming from the talk, the series of 3 talks that I gave. Okay, so let's start with set cover. So before that, let me revise the definition of max cover. We have right supernodes, left supernodes. It's parameterized by k, the number of right supernodes. We say that a labeling is picking one node in each of the WJs. So that's called a labeling, picking a representative. And we say that given a labeling, that is one from each of them, so k vertices, it covers a supernode, left supernode ui. If there is a common neighbor in ui, u in ui, which is a neighbor to all the k vertices. And then the notion of max cover is to find a labeling which covers the maximum fraction of the left supernodes. And the decision problem is, in the S case, there are k guys which cover all the supernodes. There is one common neighbor in each one of the left supernodes. And in the no case, you cover at most S fraction. And we said that it has the projection property is if you fix any Wj and Ui, and you look at the induced subgraph, it either is a complete bipartite graph in the sense that it's irrelevant, or it is like a function. So every guy in Wj has exactly one neighbor in Ui. And we showed that even with this additional property, it still is W1 hard. Okay. And yesterday we saw this hardness of approximation result, which is you start from a max cover instance with the projection property, and you reduce it to another max cover instance which has a gap. So that is, if gamma naught had max cover value 1, then you remain 1 in gamma. But if gamma naught was less than 1, so it failed, say, just one supernode, then it didn't cover one supernode, then now you no longer cover, say, roughly 1 over q fraction of the supernodes, because the log q u naught term is quite small. And you have blown up roughly by q to the r factor, where r was the initial number of left supernodes that were there. So this is an approximability result we saw. Clearly, since the blow up is q to the r, and you want q to the r to be at most n, where n is the original input problem size, so you get an approximability factor of 1 over n to the 1 over k. But then for set cover, we don't need, and in fact, we cannot afford such gaps. So we're going to see what we are doing. And in order to reach the set cover problem, we need what is called min label problem. So notice that max cover problem, as we said, is a maximization problem. You have to pick k vertices such that some objective function is maximized. Whereas set cover problem, which is, you want to cover the universe. So given a set system, find the smallest number of sets to cover the entire universe is a minimization problem. So in order to use the hardness of approximation of max cover, we need to first go to a minimization problem, which is min label, which is the natural minimization variant of the max cover problem. So it's the same exact instance as the max cover, and we have the same notion of labeling, same notion of covering, except in min label, you are no longer trying to find a labeling of W, but trying to find a subset X of W, such that for every left supernode Ui, there exists a labeling completely contained in this X, which is covering Ui. So if, for instance, there were k vertices that covered all the supernodes, you just pick those k vertices to be X, and you're done. But in the no case, if k vertices didn't cover some fraction of the supernodes, then you might have to pick some extra elements in W, such that you have different possible labelings for each of the supernodes on the left. So here you're trying to find the smallest set of extra labels you want to find. And the decision problem would be like in the S case, you just need k labels, and in the no case, you need S times k labels. So what's the connection between the max cover and min label? So there is a trivial averaging argument that goes through, which is that if you take the max cover instance, and you can think of the max cover instance as also min label instance, right? And if the max cover value was 1, then clearly there is this k guys which cover all the supernodes. So you just pick those k guys, and that is also a min label solution. But if the max cover value was at most epsilon, for some epsilon, then we'll see now an argument to show that the min label value can be at most 1 over epsilon to the 1 over k times k. So for instance, if epsilon was, say, k to the k, right? So if epsilon was 1 over k to the k, then your min label would be at least k square, because 1 over epsilon would be k to the k, and k to the k to the 1 over k is k, so k times k is k square. And so let's try to see this proof. It's a simple averaging argument, and the completeness is obvious, right? So if you had the k guys, you'll just pick the same k guys and you're done. So in the soundness case, let's say that you have a solution X. So you have picked X guys, so you have a set X, which is a subset of W, and it's a min label solution. That means that every labeling, so that means that, so let me go back. So you have picked some subset X, such that means that for every supernode on the left, you have k guys in X, one from each Wi, such that this is a common neighbor to this one of the nodes in the supernode. But then you have that every labeling Sx covers at most epsilon fraction, because we're in the soundness case, right? So every labeling will cover at most epsilon fraction of the supernodes. And if you think about it, there are just x choose k, like x size of x over k choose k many distinct labelings of W, because you want to pick one from each Wi, right? So the total number is size of x, but then each one is roughly x over k, and then you can choose one of them. So it's x over k choose k, distinct labelings. And since this is covering all the supernodes, that means that, and each labeling can cover at most epsilon fraction of the supernodes, we have that x over k choose k times epsilon is at least 1, because you're covering all the supernodes. And if you just move these things around, then if you simplify this, you get that size of x has to be at least 1 over epsilon to the 1 over k times k. So that's just a simple averaging argument. And this would give us something, but actually, if you it didn't care about where the hard instances of max cover are coming from and things like that. But if you really know that it's coming from a k-clique instance, and you open up how we created a gap and everything, we can get a slightly stronger result. We can avoid the 1 over k that's here in the exponent and get the following result, which is that you can start from a max cover instance with projection property with no gap, and reduce it to a min label instance using exactly the analysis we did in last lecture, but you need to do a more refined analysis because you're measuring the min label value. such that you get the following. So if the original max cover value was 1, then the min label value is k. The completeness holds. But if you failed, just say one supernode, if the max cover value was less than 1, then the min label value is at least q over r. Right? So there is no 1 over k in the exponent here. And the blow up is of the factor q over r, q to the r. So notice that now I can set q to be again n to the 1 over r. And then I have that the min label value is at least n to the 1 over r. And that's basically, this is better than the bound that was obtained from here, because here it would be n to the 1 over r times 1 over k. So you'll have an extra exponent factor. And we're going to need this because we're going to use this result to prove state-of-the-art set cover in approximability result. So now I want to go from min label to set cover. This is a very well-known reduction from, I think, going back to Feige. So you have a min label instance, and in particular, notice that this notation, that size of UI, so each left supernode is, let's say, of size exactly L. So the reduction is as follows. We are going to be building a set system. So first I need to define what the universe is. So the universe is just the following. We look at every left supernode UI and take every possible function from UI to the interval 1 to k. So it's all possible functions from L, because you have labeled all the vertices in UI using 1 to L. So it's all the possible functions from L to k for every supernode UI. So it's all pairs I comma f, where I is a value which gives you the index of the supernode, and f is any function which takes all the elements in UI to the range 1 to k. So that's our universe. And I'll give some intuition as to why this construction might seem completely coming out of nowhere, but there's a lot of nice intuition to this. So I'll come to that later. And then we need to define sets, right? Like we need a collection of sets. So each node in W is going to be a set in our set system. I haven't told you what that set is, but it's going to be a set. So the universe is what all pairs I comma f, and the sets are every vertex W is going to be a set. Let me complete the construction by telling you what this set is. So we take a universe element I comma f, and we say that it's in the set SW for some vertex W in W. If there exists some node U in UI such that W and U are neighbors, so there is an edge in my min label instance, and when you apply the function f on U, you get back to, say, if W was in WJ, then you get back to J. So what is really happening here is that you are simultaneously checking that there is an edge, and it's coming from that edge is sort of acceptable by the function. So each function sort of says, each function is sort of saying for each node in UI, in the supernode UI, I'm going to only check the edge coming from a particular, it has k neighbors, right? Because there are k supernodes on the right. But I'm not going to care about all the k neighbors. I'm going to just take one neighbor. And I'm going to check if there is an edge from this neighbor. So each function is sort of checking for each node in UI one of the right supernodes. And there's a beautiful geometric interpretation to this, which comes from axis parallel boxes. And it also comes from the integrality gap of set cover instances. But I'll skip that for now. But this is the construction. And let's just talk about the sizes of the set system. The number of collection of sets we have is 1 for each vertex in W. So that size of W is the size of the collection of sets. And the size of the universe, which is the more interesting component that we care about, is, so we have R supernodes, that's I, the range of I, and all functions from L to K, that's K to the L many functions. So notice that the L really, so if you want the universe to not be too large, when you start from a min label instance, you want the L to be small. And the L was precisely the term Q to the R coming from before. So you can't have q to the r to be too large because it's sitting in the exponent here. Okay. So let me give the proof of the completeness case. The completeness case, let's say that we have a labeling that covers every UI, right? So we have a labeling W1 to WK, WI is in, WJ is in WJ, like we have picked one from each of the right supernodes, and it covers every label, every supernode UI. Then we claim that if you look at the corresponding sets, SW1 up to SWK, it covers the entire universe. Why do we claim this? Take an arbitrary universe element, I comma f. Arbitrary, there's no condition on it. Now, notice that there exists some u in ui, just such that u comma wj, so that u is a common neighbor to w1 to wk. This is just because the node, the w1 to wk covers the supernode ui, and once it's covering the supernode ui, that means that there is some vertex u there, which is a common neighbor to w1 to wk. And now, regardless of what the function f is, let's say f of u pointed to some value j. Now, we know that f of u will point to j, and we know that if you look at wj, it's a common neighbor of u. Hence, I comma f by construction belongs to the set swj. So swj is covering the universe element I comma f, and we picked I comma f arbitrarily. So all the universe elements are covered using these k sets. And I'm going to do the soundness analysis right now. But before that, I want to say is that if the set cover, so if the min label instance had size k, the set cover, there are k sets that cover everything. And what we'll show next is that if the min label instance needed sk many labels, then we claim that it's the same thing here, that we need sk many sets in order to cover the entire universe. So the gap exactly translates from min label without any change. The only change is the blow up in the size of the universe by k to the L. So this is the only thing. So that's why we can't take arbitrary gap in min label and translate to set cover, because the set cover instance blows up exponentially. So if we had n to the 1 over k gap, as we talked about before in min label, we cannot allow n to the 1 over k here, but log of that we can. So we'll allow log n to the 1 over k, for instance. And that is going to be our hardness approximation result for set cover. But anyway, I want to show the soundness analysis now. So let's just recollect that the universe element is all pairs I comma f, and we put the universe element I comma f in the set SW if there exists some u in ui where it's the same I in I comma f, such that u comma w is an edge and the w is the set that it corresponds to, and f of u points to j. J is where w is. W is in wj. Now, let's assume that there is some collection of sets of size sk minus 1 which cover the entire universe. Okay, and we'll see will lead to a contradiction. Now, that means because we know that these sk minus 1 labels do not form a min label solution because we are in the soundness case, there exists some supernode ui that's not covered by any labeling. So you look at X and you try to pick one of each W1, W2, W3, Wj within X. And we know that regardless of what the labeling is, we know there exists some supernode ui which will not be covered by any of those labelings. And now if we go within ui, you look at every vertex within the supernode ui, for every node u, there exists some j in k because it's not being covered, right, by any labeling. So if you take any labeling, we know that there exists some j for which it has no edge. So if you look at X restricted to some supernode wj and you pick some u here, there will be no edges. So for every u, you can find some j such that X restricted to wj and u have no edges between them. This is just following from the fact that there exists a ui not covered by any labeling in X. And so for every u, we found this j, right? So now if I set my function f, I need to define a function f from L to k. So for every f of u, I'll define it to be this particular j. So what that means is that I comma f is not covered by x just because there will be no edge. So for every, regardless of which labeling you take, which set you take, you'll not be able to find this edge back because we made sure that there is no edges here. So we found a universe element which is not covered. So that leads to a contradiction. So size of x has to be at least sk. So what did we end up proving? What we ended up proving is that there is a reduction. It's an FPT reduction from k-clique to set cover. So we went from k-clique to projection max cover. From projection max cover, we went to gap min label. From gap min label, we went to set cover. So these are the steps that we took. But the final result is that if G had a k-clique, then k choose 2 sets are enough in S to cover U. But if G had no k-clique, then so the k choose 2 in the completeness case comes from the fact how we translated the k-clique problem as a projection max cover problem. That's why. So if G had a k-clique, then k choose 2 in S cover the entire universe. But if G has no k-clique, then you need at least log n to the 1 over k many sets in S to cover the entire universe. And your size of the set system, U and S are at most n. Okay, so this reduction runs in some 2 to the poly k poly n time. And that's exactly, also let me make a nuanced difference that this is exactly why we don't need the PCP theorem and things like that, because if you translated this to the NP world, then your 2 to the poly k would be exponential running time because your k is typically linear in n there. So this would not give you anything meaningful in NP world. This is a reduction tailored for the FPT world. And that's it. So that's we saw the inapproximability result of set cover now. Okay. So now I want to talk a bit about biclique. So let me just recap about the one-sided biclique problem. So we are given a bipartite graph, U and W, and we want to find k vertices in W with as many common neighbors in U as possible. And we showed yesterday the following reduction, albeit like we didn't show how to construct a threshold gadget, but apart from that, we showed that if you start from k-clique, you can reduce it to a one-sided biclique instance, such that if G had a k-clique, then there exist these k choose 2 vertices in W which have n to the 1 over k common neighbors. Whereas if G had no k-clique, then every k choose 2 vertices you pick in W have at most k plus 1 factorial common neighbors. If you think of k as fixed, then this is a huge gap. So we saw this result. And this immediately implies the biclique result. So for instance, let me first define what the biclique problem is, that you have the same bipartite graph, and you want to find k vertices in W with k common neighbors in U. So you want to see if there's a KKK, a bipartite graph with k vertices here and k vertices here balanced and complete, which is hiding as a subgraph in induced subgraph in UW. And we do find this thing, and so what we get is the hardness of result like this, that if G has a k-clique, then there are k plus 1 factorial plus 1 vertices in W which have k plus 1 factorial plus 1 common neighbors in U. So you have a blow up in the parameter k to k plus 1 factorial plus 1. And if G has no k-clique, then every k plus 1 factorial plus 1 vertices in W have at most k plus 1 factorial common neighbors in U. And the way this is done is quite simple. It's just we'll take the one-sided biclique instance and we are going to add on. So we are picking k right here, like it, or k choose 2. So we're going to add k plus 1 factorial plus 1 minus k choose 2 extra vertices in W and just connect them to all the vertices in U. So you can pick them for free. And then the remaining picking reduces to the one-sided biclique problem. So it just trivially reduces from the one-sided biclique problem, but you have lost all your gap. So there is the fact that we generated n to the 1 over k gap was useless It's just that we managed to do it. Now, there were a couple of more applications of the one-sided biclique problems hardness of approximation result. In particular, it was used for what is called the minimum distance of a chord problem and the shortest vector in a lattice problem. I thought of actually writing a bit and showing something, but everything gets way too technical over there. And yeah, it's very hard to make any justice to the results in short time. But let me say that, so the one-sided biclique problem, as far as we know right now, has 3 applications at least. One of them is the exact hardness of biclique problem. The second is the approximation hardness of minimum distance of a chord problem, which is where you're given a generator matrix A, and you want to find any vector x such that A times x has very small Hamming weight, has Hamming weight at most k. And we can prove, so this is a problem coming classically from coding theory. And similarly, we have a lattice theory problem called find the shortest vector in a lattice. And both of these the reduction starts from the one-sided biclique problem. So the one-sided biclique problem has a lot of applications as well. But that's what I want to show for the one-sided biclique problem for now. I want to now show a bit of the hardness of approximation of clique result. So we don't know how to show hardness of approximation of clique W1 hardness. So what I'm going to show now is going to be based on an assumption called gap ETH. So gap ETH assumption is this, that if you look at 3SAT, and if I make a promise that either your 3SAT instance has a satisfying assignment, or the 3SAT instance, every assignment fails at least delta fraction of the clauses. If I make this promise, even then, there is no algorithm that runs in, say, 2 to the little o of n time, which can decide whether the instance is satisfiable or fails delta fraction of the clauses. Or more formally, it says that there exists some epsilon and delta, which are absolute constants bounded away from 0, such that no algorithm can solve this 1 versus 1 minus delta gap 3SAT problem, that is, decide whether it's completely satisfiable or fails delta fraction of the clauses on n variables, running in time 2 to the epsilon n. So you need to run at least in time greater than that in order to decide. So this is the gap ETH hypothesis. It already has the gap inside it. So all we have to do is translate the gap. And now we are going to see a reduction to approximating clique. In fact, we'll prove a quite strong result. That assuming gap ETH, we are going to rule out all FPT algorithms. So all algorithms of the form T of k times poly n for any computable function T. So we want to rule out FPT algorithms to distinguish between the following 2 cases. In the yes case, we are given a graph and there is a k clique. And in the no case, we are given a graph, but there is no log k clique. So there's a huge gap. And we'll see the proof of this result now. So we are starting from gap ETH, right? So that means we are starting from a 3CNF on n variables and Cn clauses. And for every I in k, so we are going to look at k collection of clauses. We are going to build C1, C2 up to Ck. These are all collections of clauses. Each has dn over log k clauses that we pick randomly, where d is some very large constant that we'll fix later. It's a universal constant that we'll fix later. It will depend on C. So we are given a CNF formula. We construct k many collection of clauses. And in each collection, what we do is we uniformly and independently pick dn over log k many clauses at random. Okay. And once we have this collection of clauses, C1 to Ck, each one containing dn over log k many clauses, then we'll construct a graph G, and it will be on vertex sets V1 to Vk. So we'll have a collection. So we'll have a collection independent set V1, an independent set V2, independent set V3, so on, up to an independent set Vk, and we'll just have edges between Vi and Vj, and we're going to tell what these edges are. So first, let me say what these vertices represent. So it's V1 is a collection of vertices. So each Vi will, so you basically look at the collection of clauses in Ci, and it has some partial assignments that satisfy all the collection of clauses that we have there. And for each satisfiable partial assignment, we create a vertex in Vi. And once we do that, then we take two vertices, one in Vi and the other in Vj, both corresponding to partial assignments, but for a different collection of clauses. However, these two different collection of clauses may share some variables in common. So these two partial assignments are assigning values to a common variable. And if they're consistent on their assignment, then you put an edge between Vi and Vj. And also note that we can do some pre-processing on the GapETH instance such that each variable appears in a constant number of clauses. So if each variable appears in a constant number of clauses and we picked dn over log k clauses, then there are at most O of dn over log k variables appearing. So the number of partial assignments is 2 to the O of dn over log k. So size of Vi is bounded by this. So you have built a graph on k times 2 to the O of dn over log k vertices. And now we just need to argue about cliques in this graph. Okay. So in the completeness case, suppose we had a satisfying assignment. Okay. So if suppose we had a satisfying assignment, then all we do is we pick Vi. So we look at the satisfying assignment sigma, and in Vi we'll pick one vertex. Which is this vertex? It's look at all the variables appearing in Vi. So you have some Vi corresponds to some collection of partial assignments of clauses in Ci, right? So you look at all the variables appearing in Ci, and you restrict sigma, the value of the assignment, to those variables. Those variables will appear as a partial assignment. This assignment will appear as a partial assignment in Vi just because Vi contains all the partial assignments that satisfy all the clauses in Ci. And so you pick that vertex. And this forms, if you just pick one from, so you picked one vertex in each Vi, this forms a k clique. So because you have picked k vertices, and everything is consistent because you're building them from a global satisfying assignment sigma. So you have there is a k clique in the graph. So that's the completeness. Let's say the soundness. So in the soundness, we know that any assignment to phi will fail 1 minus delta fraction of the clauses. And now the observation we have is that in the way we built these C1 to Ck is that if you take any collection of log k, so you don't pick, so we have k many collection of clauses, and we pick just say log k of them, which call them Ci1 up to Ci log k, and you take their union, then it contains at least 1 minus delta over 2 fraction of the clauses of phi. Why is this? Notice that each Ci1 contains dn over log k. So if you take log k of them, you expect about dn many clauses, right? And you can just choose your d to be sufficiently larger than c, so that you have, like, with very high probability, 1 minus delta over 2, like almost 1 fraction of all the clauses that we have. And because we have this, now if there was a clique of size log k, let's call it Vi1 up to Vi log k, then because it's a clique, it means that it's consistent on all the variables that appear within, right? And we know that the number of clauses it's satisfying, just because these are partial assignments that satisfy all the clauses within that collection, the number of total clauses satisfying is 1 minus delta over 2. So we found a consistent assignment, global assignment, that satisfies 1 minus delta over 2 fraction of the clauses. And this is a contradiction because we assumed it satisfies at most 1 minus delta, not delta over 2. So there is no log k clique. And finally, so we have showed basically that before, what we have shown here is that if there's a satisfying assignment, you have a k clique. If there is no satisfying assignment, in fact, if every assignment fails 1 minus delta fraction of the clauses, then you don't have a log k clique. So from this, the time lower bound follows, because if you had a T of k poly V algorithm for gap k clique with these perimeters of gap, then because we bounded size of V by 2 to the O of dn over log k, we have a T of k 2 to the O of dn over log k algorithm for 1 versus 1 minus delta gap 3 sat. And now if you just choose your k to be sufficiently large, right, like 2 to the exponential in epsilon, then you will have an algorithm running in time less than 2 to the epsilon n for solving gap 3 sat, which contradicts gap ETH. And that's basically the proof of hardness of approximation of clique. But again, I want to note that we used the fact that there is a gap. And this is not the most desirable thing to do. Okay. So I want to talk of now a few open problems. So if in the first lecture, I remember quoting one of the slides from Parsons showing the summary of the results. And really the interesting part is here, which is we have these assumptions called gap ETH and PIH, which I'll refer to soon. And we can prove a lot of strong results based on them. Like for instance, the inapproximability of k clique and k by clique, all these things follow from gap ETH. And this is not really desirable. So an broad umbrella open question is to sort of get rid of the dependency on gap ETH. So if we have proved the hardness of approximation result for some problem based on gap ETH, can we prove the same result using ETH? Or can we do even better using W1 not equal to FPT? So this is a big umbrella open question, but I want to raise specific questions which are of interest to me at least. So the first question is that whether is it W1 hard to approximate the k-clique problem to a factor of 1.01. So I'll give you the fact that, say, in the yes case, there is a k-clique. In the no case, there is no 0.99 k-clique. So, or even say, let there is no k over 2 clique. Is this problem W1 hard? How do we prove this? There are many technical challenges in order to prove this kind of a result. And a more broader question would be, let's say we have ETH, which is defined, which is exactly gap ETH, but without the gap, that there is no algorithm for 3 sat running in 2 to the little o of n time, or more formally, there exists some epsilon such that no algorithm can solve 3 sat on n variables in 2 to the epsilon n time. And we recall gap ETH. And then does gap ETH follow from ETH? So clearly, if what is known in literature as a PCP of linear proof size length, if it existed, then this holds naturally. But we don't know if it exists. And it might be the fact that gap ETH following from ETH is an easier problem to resolve than constructing said PCP. And there has been some non-trivial progress on this as well. And it would be interesting to resolve this completely, because then all the results, like for instance, we would have that ETH would rule out k over log k approximation algorithms for the k-clique problem. In FPT algorithms for the k over log k approximation FPT algorithms for the k-clique problem. And that would be much reasonable, because ETH is definitely much more standard assumption than gap ETH. Okay. So then we have also what is called PIH, parameterized inapproximability hypothesis, which is actually, if we recall the label cover problem that we had, which was initially introduced in the NP world, it's exactly the label cover problem, except the number of variables is a parameter, is a fixed parameter, and the input is really the alphabet size. So that's exactly what this is talking about. It's saying that that problem is still W1 hard to approximate, or you can think of it as a 2 CSP. So a CSP where all the constraints have arity 2 on k variables and n alphabet. Is this hard to approximate? So in the yes case, there will be an assignment k to all the k variables that satisfy all the constraints, and in the no case, any assignment to the k variables fails at least 0.01 fraction of the constraints. Is this problem still W1 hard? And PIH is definitely implied from GAP-ETH. So proving this would already give us a few of the results. Like for instance, the K-clique result would be given to us. So this is already a very important direction. And in particular to the set cover problem, there is still some fine-tuned results we want to expect. One is we have no techniques to prove W2 hardness of approximation results. So all we showed now was that set cover was hard to approximate to in assuming and showing W1 hardness for it. But set cover itself is a W2 complete problem, exact set cover. So can we show even just that approximating it to 1.01 factor is W2 complete? So is approximating K set cover to 1.01 factor W2 hard? And I didn't mention this, but if we look at the reductions that we had, then there is this notion of locality that we use when we created a gap. And that is precisely the reason why we can't start from set cover. Like there is no way to write set cover as a max cover instance with projection property, but we can write K-clique as a max cover instance with projection property. And we saw why, right? Like because max cover is inside W1. So if we had a reduction from set cover to max cover, that would imply W2 equals W1. So we need a new technique and framework altogether to prove this kind of a result. And we can also ask for better inapproximability factors. Right now we are stuck at log n to the 1 over k, and we can improve that 1 over k to any 1 over h of k for any function h. But still, we can't rule out little o of log n approximation algorithms in running an FPT time for k set cover. So is it still W1 hard? Because in the NP world, there is no polynomial time algorithm for this factor. So does it hold also for FPT algorithms? Finally, we can look at the maximization variant of set cover, which is called the max coverage problem. Given you can't now, you don't choose how many sets, you have to pick exactly k sets, and you ask what fraction of the universe can I cover. In the yes case, it will be 1, and in the no case, we want to claim that you can cover at most 1 minus 1 over e fraction, which comes from the standard greedy algorithm. And is it W1 hard to approximate it beyond this 1 minus 1 over e factor? We don't know. We can show this result assuming GAP-ETH, but we would like to ideally show it using W1 hardness. So this is another important question. Also because this result immediately implies that k-means and k-median hardness of approximation results under assuming W1 not equal to FPT. So for instance, this problem immediately says that the k-median problem in general metrics is hard to approximate to factors 1 plus 2 over e by algorithms running by FPT algorithms. So this is an important problem for that result. And finally, we showed exact hardness of biclique, but we don't know how to show any hardness of approximation result. Again, it's implied from GAP-ETH, but we want to show assuming W1 not equal to FPT. So proving hardness of approximation results for biclique is also an important problem. Of course, this is a harder problem than showing W1 hardness for approximating K-clique. So this would be like thing after K-clique. And finally, I made a few comments earlier in lecture 1 and lecture 2 that these one-sided biclique and max cover are very related problems. In fact, one can be seen as a coloring version of the other. And I also said that the color coding method immediately reduces one-sided biclique to max cover. What about the other direction? Can we reduce max cover to one-sided biclique? That is, can we remove the color classes in the max cover instance, the W1, W2, Wj? Can we get rid of them and ask for picking any k vertices? And there has been some work on this. And this leads to very beautiful geometric embedding theorems and uses a lot of nice algebraic geometric structures. So this is just very interesting from a mathematical point of view, but also it's a very cool philosophical question. Color coding is a very important algorithmic technique. Is there a reversal of the color coding technique? That if you had a problem with all these color classes, can you reduce it to the same problem without the color classes? And that's a nice meta question to tackle on its own. Anyway, so that's my time, and I've left some room for questions.
Thank you so much, Karthik.